Okay, we are online now. Okay, so the initial, my problem has an initial height of 8 feet, but it wants the output of this function in inches. So the initial value for my function is going to be 8 times 12, or 96 inches. Okay, and then what's going to be my growth or decay factor? Is this growth or decay? It says each bounce rises to 80% of the height from which it fell. Growth or decay? So is this 96 going to increase or decrease with each bounce? Decrease, that's decay. So the question is, what is my decay factor? 0.8 or 0.2? Remember, what we want for the value of b is what we keep. It's the amount that we keep. And that's what they're giving us. They're not giving us the percent lost. They're giving us the percent kept every bounce. Do you see that? So this is going to be 0.8. So we can use our exponential form. Our input is n, so it's going to be 96 times 0.8 to the n. How high will it be on the 13th bounce? Well, with every bounce, what happens every time it bounces to our original 96? Every time it bounces, what happens to the original 96? What would that represent? 96 times 0.8. Pay attention. Okay. What's that? What is 96 times 0.8? What does it mean? What would that mean? And what would that, in this problem, what would that be? 80%. The height of the ball on the first bounce, right? After the first bounce. So that's what's happening. Every time we have a bounce, we take 80% of what we had before. So by the 13th bounce, how many times will we have taken 80%? 13 times. That's how the formula works, right? 96 times 0.8 times 0.8 times 0.8. For every bounce, 0.8 of what you had before. 80% of what you had before. Right? The exponent is just to make it shorter. That's all the exponent is for, just to make that expression shorter. We don't want to type 0.8 13 times. Okay, so this is the kind of more of the question for the new stuff. So we want the ball to rise no higher than 1 inch. 1 inch. Input or output of our function? Output. Okay? So we're going to say h of n is going to equal 1. And we want to know what n does it. Right? So we want to know how many bounces until we get to an inch. All right, so when we're now just trying to solve for the exponent, first step, divide by 96. 0.8 to the n. Okay, so what is n? N is the exponent of. So I'm really hoping that you're coming to situations like this in these problems. Now you're applying this new knowledge you have about solving for exponents. Say it out loud. N is the exponent of 0.8 that gives 196. So we can write it. N is, exponents are logs. N, see, look, you can just read it left to right. N is the exponent of 0.8. That gives 196th. If you learn to take the log of both sides and you cling to that and you love that, well, I just saved you 2 steps. We just made it to our answer much faster than taking the log of both sides, just by understanding what a log is. Okay? Again, n is the exponent of 0.8 that gives 196. Read it from left to right. And now we need a value for that. And that's where our change of base formula comes in. Right? So you got the built-in buttons on your calculator that do base 10 and base E. Take your pick. I'll do base 10. Log of 1 over 96 over log of, and I think even I'm guessing, and I don't know for sure, but I'm guessing that, yeah, it even has it. So log, it's the same meaning without the base there. The meaning is base 10. So you can do 1 over 96 divided by log. Oh, wait, but we need a whole number of bounces. This isn't going to work. We've got to get a decimal approximation and then think about this. So anyone got a calculator? Anyone got this? Get a number. Log of 0.8. I got 20.45. Is that what you got too? So you can't have 20.45 bounces. So the question is, at 20 bounces, is the 20th bounce greater or less than an inch? The 20th bounce. It's got to be greater. They're getting less, right? The height is getting less with each bounce. So if you're if you have less bounces than that, and this is equal to 1 inch, then that's got to be greater than 1 inch. And so to make sure we're below 1 inch, how many bounces? 21. 21, right? So we need that next bounce to assure that's less than an inch, right? This is going to still be, that is an inch, so the 20th bounce would be 1 point something inches high. All right. Green bar. So this is what I'm hoping for at least some of you to have learned. This right here, that you come to the place where you need the exponent and you use logs because of their meanings. They're exponents. Adam.
Are we allowed to email you and ask for more tries?
No, email me before your tries are up. Email me after 2 tries or 3 tries, and then I'll help. I mean, yeah, occasionally I'll do that. Occasionally I will extend tries. Yeah, but if you're at 2 or 3 tries and it's not going well, then email me. Make sure that, yeah, get the help before your tries are up. But yes, occasionally I'll give you a few more tries. Okay, other questions on this one? Okay, next one. All right, so we got town 2000. Okay, so from 3562 in 1970 to 1965 and 2000, and we want t to be the number of years. Okay, so we're going to have a, b to the t. What will a be? So we need to find a, and we need to figure out b. A will be, that's easy. That's the population in 1970. So now the question is, what is the growth factor that we need? So how am I going to get this growth factor? I know that here we go 3562. I've got, 1970 is my initial, and then 30 years later, 9765, and I need what? The 1 year growth factor. So what can I get first? And the 30-year growth factor, how do you get that, Jessica?
Divide 9,765
Uh-huh.
by 2,165. And then take that answer into the 130th.
That's right. So this is the number that you'd multiply 3562 by to get 9765. So that's our 30-year growth factor, right? And so then we want the 1 year growth factor. So to the 130th. And then we need the annual percent change. So let's go ahead and find that as an approximation. So I want 9765 divided by 3562 raised to the 1/30th, 1.03419. Okay, and so what happens in the way that this problem was coded, you can do an approximation and get A right, but then when you use it for part C, it won't work unless you have this much precision. So I put a request in to have them kind of loosen the precision on C, so make it more friendly to rounding. But that's, if you got C wrong, that's probably what happened. So let's go ahead and just put that whole thing in there, 1.03419, because that's our 1 year growth factor. Okay, annual percent change. Is it growth or decay? Growth, and we can just get it by looking at this. This is easy. 3.419%, right? That's how much it's going up every year. User function to get the population in 2019. So we can just take that output, put it here, and then we just need to know what T is for 2019. How many years after 1970 is 2019? Is that 49? 49? Okay, so then here's the most important question for the new stuff. So 40,000 is our output that we want. We want to know how many years. It takes to get that amount of output. Okay, so we're trying to solve for T. First step, divide by the 3562. Okay, and so what do we got? T, say it. T is the exponent of? Is the exponent of what? 1.0349. T is the exponent of 1.039. That gives that ratio, right? So mathematically, T is the exponent of 1.03419. That gives what? Tell me. Yeah, I am. Why don't you know? Well, that's not the reason you don't know right now, though. Okay, so it gives this. T is the exponent of that base. That gives this, and this is what this says. T is the exponent of that number. That gives that. So much easier than taking the log of both sides. But now we need what? We need a good approximation. So I'll use ln this time. ln of the ratio over ln of 1.03419. So we only had like 1 or 2 examples of this, and that's why I want to take the time to show this process. Because all the stuff we did with logs was we started with the log, and we practiced rewriting it as an exponential. But really, when you're solving problems and you're trying to get an exponent, then you need to write that exponent as a log and then use your change of base to get the value. So we need practice on that too. Any questions? Let's just see what that is. So we want natural log of that thing. Will it let me do that? Good, okay. Divided by natural log of 1.03419. 71.94. So we want the population it's increasing, right? So this is growth. And so in what year? So in what year? It's going to reach that in the 79th? Or sorry, 71st? Or in the 72nd year? 72nd, right? So after 71 years, t is 71. And so then that next year from 71 to 72 is the 72nd year. And so it's in that year, so we want 1970 plus 72. You can even put your answer in like that. That's because that will be the year that this happens. 1970 plus 72. Is that 2042? But I'll just leave it like that. Okay, questions on that one? Okay, one more, and then we'll take the quiz. So this last one, it gave you the function, but like in a different form. So t, so this is a voltage, and it's giving you this function 4 times 2.72 to the negative t over 2. And where t is in seconds. So I'm going to go to part B first. So the 1 second growth factor is what we would have in the parentheses if we rearrange this to have t as the exponent. So remember that whatever your unit is on the exponent will match with the growth factor of that whole base. So we just need to rewrite this function as something to the t. And what do we have? We have 2.72 to the negative t over 2. Okay, so what do we really have inside? So we could separate out the t. This is t times what? Negative t over 2 equals to t times what? 2.72 to the negative 1/2. So now, when you multiply those two together, you would get that negative t over 2. And now, so what's the 1 second growth factor? It's this. 2.72 to the negative 1/2 is our 1 second growth factor. And this is equal to, this is just a different way of writing VT. To figure out what that growth factor is, you're saying what raised to just the plain old t, that would be the 1 second growth factor, again, because what's in that parentheses has to agree with the units of that. Okay, so this is also the same as 1 over the square root of 2.72. So 1/2 is square root, negative exponent means denominator. So that's 1 over the square root of 2.72. So I'll just do 1 divided by, I'll do square root. Exact answer, so that'll be an exact value. Voltage after 2 seconds, you're just going to do V of 2, right? It'll just be V of 2. All right, so then one more practice of so let's have, so when will the voltage be 1 volt? When will the voltage be 1 volt? Output or input? 1 volt. Output. So we're going to get 1 equals 4 times 2.72 to negative 1/2 to the t. All right, so I want you to practice solving it the way that I've just shown 2 examples and we did one last time. So can you practice, see if you can solve for t without taking the log of both sides. Without taking the log of both sides, solve for t. See if you can do it. Everybody. And so this thing right here is just a number, so you can just keep writing it like this, and just think of it as this is one number, and you can just keep expressing it as that entity. Okay? Don't let it scare you. Solving for t. Everyone try. Who's going to be the lucky winner? Okay, Chris, did you get it? Walk me through it, not just the answer. So what'd you do first? Are we ready to write t as a log? We got one step before that. No, because that's the base. That thing is to the t, so those are locked. But we got to get this thing by itself, right? Divide by 4. So we do 1/4. Okay, now we're ready to write out what t is. Tell me what t is. Kennedy, did you get it? What is t? Beautiful. Beautiful. It's the exponent of that that gives that. So how can we write that? Express that. That's what it is. So just remember, it's that base. Don't let that scare you. It's an expression. It's okay. But it's just a number, right? It's just a number. That whole thing is the base. Okay? And then we need our change of base. Take your pick. What are we going to use? Kennedy, keep going. Common log, okay? Yeah, the way you can remember is the base we put down lower, that's the one that's going to go in the denominator. And the one that we're taking the log of, that's up kind of higher, that goes in the numerator. So if you want to define a decimal approximation of that, the 1 second growth factor, that's easier for you, that's totally fine. Just make sure you keep enough decimal places through the process. But also know that you can express numbers in lots of ways, not just as a decimal approximation. We got 2.77084. So when will the voltage be 1 volt? Now seconds, what is seconds? Seconds is a continuous quantity, right? It's continuous. So we're not going to either choose 2 or 3 this time. So we can actually have a part of a second, right? That makes sense. So 2.7708, try. .7708 is what this equals right here. Just make sure those two are right. Got them. Okay, questions on using logs to find values of exponents. What are we doing? Logs are exponents. We're rewriting those exponents as a log and then using the change of base formula to get approximation. That's what I want you to take away from this. Any questions before the quiz? Okay, so we're going to move on to Module 5. So we'll do a little bit in Module 5 today and then Tuesday after break, and then your exam will be on Modules 4 and 5. So most of the exam will be Module 4, okay? But then there will be the stuff we do today and that Tuesday when we get back. And so let's talk about that. So remember on the first week of class? First week of class, we said if you could summarize the course in one word, it would be what? A course about what? Anybody remember? She remembers quantities, right? Quantities. And then if we were to do a little better than that and say it in 2 words, does anybody know how we could say it in 2 words? What kinds of quantities are we talking about in this course? Someone said it. Changing quantities, right? Changing quantities, right? So we have, like, we think about x increasing, and then what happens to this other thing, and that kind of brings us to even more detailed phrase of what this course is about. So not just about changing quantities, but anyone want to give a stab at it? So if we want to get a little more specific than changing quantities. So it's about how 2 quantities change together, right? How 2 quantities change together. We've looked at graphs, right? As x increases, what does the output do? Exponential, we spent a lot of time in tables, right? So as you increase by so many units of input, how's the output changing if it's exponential growth, okay? So how do 2 quantities change together? So that's what, in a word, we call covariation. Covariation, so 2 quantities changing together. So an example of covariation, we didn't look too much at this, but this should be familiar, is proportionality. So what stays constant in proportionality? Well, any corresponding pair of values of two quantities maintains a constant ratio. That's proportionality. And so we could say that y equals the one quantity is always a constant multiple of the other. What was another type of covariation that we looked closely at the beginning of the course? Remember? We spent a couple weeks on it. Two or three, actually. Remember what the first kind of big unit was about? What kind of covariation? Anybody? Extra credit. Hey, you got it. You got it. Brighton got it. Constant rate of change. Let me see. Shoot. So I want to come over here. Let's do this. So what stays with constant rate of change? There's something that stays constant. That's this first column. What stays the same in constant rate of change? Let's see if this worked. Oh, it worked good. Okay. So what stays the same when you're talking about constant rate of change? What is constant? The rate. And how do we express the rate, right? So the rate is constant. How do we express the rate? Have we learned anything? What is it? What do you think?
Constant ratio?
Of what? Yes, constant ratio of what? Is it y over x? Is it the corresponding pairs of the quantities themselves?
The change in y over change.
That's right. The changes are in a constant ratio, right? The change in a constant ratio. And then we came up with a... that's not what I wanted to do. Sorry. Okay, and so then we came up with a point-slope form. Remember, we came up with a point-slope form based on constant rate of change. That the value of one quantity is always a plus k times x minus b, where x is the corresponding value of the other quantity. That was our point-slope linear form. So the ratio is always of changes is constant, and we can write one quantity in terms of the other in the point-slope form. Okay, what's another type of covariation we've investigated? Thank you, exponential growth. And what stays constant in exponential growth? Percent change, and also growth factor. So it's like the next output divided by the previous output, right? So the next output divided by the previous output, that's our growth factor. That's what stays constant. And we know that we can write the relationship between the two quantities as y equals a b to the x. Okay, so this is kind of a summary of what we've done so far. So now we want to look at kind of covariation in general in terms of maybe creating a graph or just talking about not necessarily a particular mathematical type of covariation, but just really wrestling with how do two quantities change together given a situation. Okay, so this is the idea of modeling the covariation of any two quantities. So not necessarily constant rate of change, not necessarily exponential growth. So we're kind of letting go of a kind of the confinement of a mathematical relationship and just saying the covariation of any two quantities that we could be talking about. Okay, so the first thing we need to do is we need to identify which is going to be independent and which is going to be dependent. Or maybe if we're thinking in terms of functions, which is going to be the input and which is going to be the output. Okay, and so then conventionally we put our input variable independent on the x-axis and our result or output or dependent variable on the vertical axis, y. Okay, now here's the key. So now we're going to look at, to kind of figure out what the covariation is like, we're going to look at small equal increases of x, our independent quantity, and we're going to look at them one at a time. Okay, so we're going to say let x increase a little bit, and then we're going to ask some questions about y, and then let x increase another little bit, and then we're going to ask similar questions about y, and we're going to keep doing that. And then we're going to track what y is doing for each little increment of x. So this is very much the spirit of calculus, okay? So the first thing we're saying, just, if we increase x a little bit, what does y do? Does it go up? Does it stay about the same? Does it go down? So that's a simple question, right? Does it increase or decrease? And then does it increase a lot or a little? And the second question we're going to ask is, when we start doing this successively, we're going to say, how does the current change in y compare to the previous one? Did we get a bigger change in y than the previous? Did we get a smaller change? Was the change the same? Okay, and then from that, then we deduce, based on how the changes are changing, then we can conclude what's happening to the rate of change. Okay, as long as we're keeping those changes in x the same. If we're keeping those changes in x the same, then what's happening to the changes in y is going to predict what's happening to the rate of change. Okay, so these what I'm saying is these have the same answer, right? So if we're comparing changes in y with a consistent change in x, then the rate of change is the result about the rate of change is going to come right out of that. So the kind of the focal question here then, I mean, A is absolutely necessary, but B is kind of the focal question for us. What's happening to the changes in the output or the changes in y as we increase x a little bit at a time? Okay, so students who can articulate these things in different situations really understand covariation, okay? And then you have something to understand around all the number crunching, right? Any questions on that? So this is going to be today and on Tuesday we're gonna live in this. So if you don't remember it, you have it written down and have it as a reference. So we can maybe talk about this as, this is called like incremental thinking, incremental analysis. Please.
So are you proposing this part of the workshop on
You mean like a video?
No, I mean just the slide, just this information.
I've never posted slides, but I post the videos. But if you're interested in the PowerPoint, I could just email you the PowerPoint if you want.
Yeah, that'd be great.
Yeah. Okay. All right, so let's try an example here. Okay, so here is a bottle, and we've got, it says, examine the bottle given below, imagine the bottle filling with water. Make a possible rough sketch of a graph of the height of the water in the bottle as a function of the volume of water in the bottle. So here's what you don't want to do. You don't want to just say, oh, I know what that is, and I can draw it right now. So we want to, even if you know the final result, we still want to practice this process, because in situations where it's harder, you need the process to be able to sketch the graph in the end. So we're going to start with an easy one. So don't jump the gun and don't try to anticipate anything. Just go with this, learning this new kind of way of working this out, so we can practice it. So what do we want to do first? The first thing was to determine which is going to be input quantity and which is output. So what is our input quantity? They're giving you lots of cues here. What's the input quantity? Is it going to be the height of water in the bottle or the volume of water in the bottle? Yeah, remember our language. So something is a function of something else means that that the first thing is dependent on the second. So that second thing is kind of where we start. That's our input, and then you can see they've already labeled the axis down here, volume of water. Okay, so that's going to be the volume of water is going to be like our x, or you're used to as x. And then therefore the height is the dependent or resultant. And that should feel natural, because it's like, what do you do first? You put water in, and then what happens? You get a height out of it, right? So what happens when you put water in? And so what are we going to do? So we're going to consider, are we going to consider small amounts of volume at a time or small amounts of height at a time, according to what we said? We're going to look at small changes in x, small equal changes in x. And so we can use this grid to mean those small equal changes. So like every time, this is the small equal changes. All right, so then we'll take the first change in x, and we ask, what happens to the height? Does it go up? Does it go down? Does it stay the same? What's going to happen when we put a little bit in? Alex? This is the way to get called on in class. Okay? If you want to get called on in class, that's an easy way. How about Jesus? We're going to put a little bit of water in. What's that? It's going to go up, right? Some amount. So we'll just say like about this much, say. So we're going to put that change in x in, and it's going to go up. So we got a change in x, so you call it x1, delta x1, and that's like our delta y1, and that gives us a new point on the graph. So here we are. What do? We put the next little change of water in, or next little amount of water in, same amount as before. What's going to happen to the height? Up, down, or stay the same? Going to go up. So that's question one. Question two is, how does this increase in height compare to the previous increase in height based on this bottle? So how will it be the same? Will the change that we get for this amount of water, the second increment of water, will that change be less than the first change, the same as, or more than the first change? Okay, so I heard everything at first, but then there was kind of maybe more. So we're going to put that first amount of water in, but I'm going to put the second amount, same amount of water. Why more, James?
Because the bottle is decreasing in width.
Okay.
So if you're adding the same amount of water, it's going to be filling up higher in the bottle.
That's right. You're going to get a bigger change than you got the first time. So our delta y2, delta y1 is going to be less than delta y2. y2 is bigger, right? That new change is going to be bigger than the one before. That gives us a new point in the graph. Okay, then we're going to add another little change of water. the little amount of water, same as before. And we're going to get some change. So first of all, what will happen to the height? Up, down, or stay the same? It'll go up. So the amount that it goes up, more or less than the previous amount, delta y2. More again, because the bottle keeps getting narrower. So delta y3 is bigger than delta y2. And this is going to continue for most of the bottle. So what's happening? The changes in height are they decreasing, staying the same, or increasing? The changes in height. The changes in height are increasing. But that's a different question than what is the height doing? Is the height itself increasing, decreasing, or staying the same? The height itself. It's increasing, right? So that's just the y value. But then there's a separate question that says, what are the changes doing? Are the changes increasing, decreasing, or staying the same? And they're also increasing. So look, we're putting in equal amounts of water, and we're getting a bigger change in y each time. Is it constant rate of change? Is it constant rate? No, because what was constant rate of change? Consistent changes in x result in equal changes in x result in consistent changes in y. Well, that's clearly not what's happening here. The changes in y are getting larger. And so, what kind of graph do we get from that when it's not constant rate of change? So constant rate of change gave us a straight line, right? When you had consistent changes in y, you got a straight line. But now with growing changes in y, you're going to get curve, right? It's going to be curved. So here we have y is increasing, and the rate of and the increases are, so y is increasing. Changes in y, delta y's, are what? Increasing. So what about the rate of change of y with respect to x? Then the rate of change of y with respect to x is the rate of change then comes right out of what the changes are doing. If you have equal changes in x, which we're forcing equal changes in x, the rate of change will do the exact same thing as what the changes do. And so what are the changes doing? Increasing, therefore the rate of change is increasing. Don't follow his lead. That's one of my pet peeves. Yeah?
So do we never consider that the amount of water that we're putting in the bottle is the same? Like we never consider that part stays the same?
We're in control of the independent variable, the volume. So we're forcing equal amounts.
Yeah.
If we didn't do that, then bets are off. Like it's hard to do an analysis of the y's. So we're in control. We're saying, okay, we're going to put 2 milliliters in. I'm going to put 2 milliliters in again, and I'm going to keep putting 2 in. And that gives us a fighting chance to understand how y is changing. But I don't know if did I ask you your question?
Kind of. Yeah, I guess I was wondering why one of the questions weren't like the change, not the change, but what we were controlling the same, but I guess it's obvious.
Yeah, so so our focus is what is happening to that y quantity. And if we want to know what's happening to that y quantity, the only way we can really know for sure is if we control the x quantity to be equal increments. That's the bottom line to it. Okay, so this time I'm going to draw a graph, and you're going to do the same analysis. And then after you do the analysis, yeah, so let's just do that first. So I'm just going to draw a graph. No. I'm going to try again here. Let's try this. Okay. Okay, so there's 3 parts. Part A, part B, and part C. And just go with the spirit of what I tried to draw, right? What's the spirit of what I tried to draw? Which is, that's worse. Try again. Wow, it really wants to go up, is it? 'Cause I'm, ugh. There we go. That's good. Perfect. All right. So A, B, and C. So what are you going to do? You're going to look at equal. That's pretty good. Equal changes in volume of water added. And then you're going to look at the resulting changes in height for each part of the bottle, and do like two. You got to do like three, at least three changes of volume in each. And then you're analyzing the resulting changes in height, and you're going to do that 3 times for the A part, B part, and C part. Okay, so is the task clear? So what was our checklist? A. So when you add equal increments, what happens to Y? What happens to the height? Okay, and then second question was, what happens to changes in Y? And what's happening to the rate of change of Y? Okay, take 5 minutes and do this. So you're doing those. So for equal increments of X, you're asking those 3 questions for all 3 parts, all 3 things here.
Is part B,
Go with the spirit of what I tried to draw.
it's curved, right?
Go with the spirit of what I tried to draw. If I want it, yeah, if it's going to be curved, it's going to be curved. But what's hard to do?
That sounds scary.
Doing my best here. I need to just make this graph with, okay, there we go. That's the best I can do. Okay, Megan. Is this Megan on the? Which one's Megan? Sorry. So Megan, what's happening in part A of the bottle? Let's go to question 2. What's happening to the changes in Y in part A of the bottle? The changes. The changes are increasing. See. So Megan and, I forgot. Nasia and Lauren. So do you agree with Megan that the changes in part A are increasing? Agree with that? Nasia? Changes are increasing. What do you think? Yes. Christian, changes are increasing in part A.
Yes.
Yes. Scott, agree? Why? Tell me. Okay, why are that? So talk about the changes, and then we'll conclude about rate of change. So what about the changes?
Change stays the same.
Okay, right. So here's the change in x. Here's a corresponding change in y. Another change in x. How does that change in y compare with the first one? Is it greater? We're comparing that amount of positive increase with that amount of positive increase. And then with that amount of positive increase. What's happening to the changes? They are staying the same. The changes, y is increasing. The height is clearly increasing. As x increases, sure, y is going up. But I'm asking about the changes. Those changes stay the same. So for equal changes in x, we're getting a consistent change in y. Therefore, in part A of the bottle, now what kind of rate of change do we have? Constant rate of change. Okay, so part B of the bottle. What's happening to the changes within the section of part B of the bottle? So let's see. Bill, what do you think? So in this part of the graph, starting here and ending here, what happens to the changes in y? What's that? Changes are decreasing here. Changes are decreasing. Agree with that? David, what do you think? What's that? So I've got decreasing and increasing. In this part of the bottle, the changes in y.
I said increasing.
Oh, now you want increasing.
No, I said increasing.
I'm sorry, you said increasing. So they're both saying increasing. What do we think? Yeah? They're increasing? Everyone agree? I thought you got the point that I was trying to draw a straight line. They're not increasing. The changes are staying the same.
Wait, you said it was curved.
No, I did not say it was curved. I said I'm trying so hard to draw it straight. If I'm going to draw a curve, it'll be curved, okay? This is curved. That is straight. That's the best straight line I can draw on this thing. That's the best straight line I can draw. Look, how does that compare with this? They're the same. This change here is the same as this, is the same as this, is the same as this. Okay? This is curved. Okay. All right. What about this part of the bottle? What about the changes here?
I don't even know what
Okay, well, that's too bad. Javier, why? Yeah, the changes here are getting smaller. This change is clearly larger than, say, this one up here and this one up here. So these changes are getting smaller. What's the height doing? The height is increasing, but the change in height each time is getting smaller. Okay, so now if we wanted to draw this bottle, how would we draw this bottle? So part A of the bottle is gonna, what will it look like? If equal changes in water give us equal changes in height. Yeah, so, yep. Okay? And then what about in this part of the bottle? Okay, right, so it's going to be narrower because for the same amount of water, we're getting a bigger jump. But the jumps are, the increases are staying the same. So does it get narrower gradually or abruptly? Abruptly, right? All of a sudden now, the same amount of water is giving us a bigger change in height. So that's going to look like this. Okay? And then what about in this last part? So for equal increments of water, we have decreasing changes. What's that gonna do? Wider. Yep, it's gonna flare out, right? So everybody has a bottle like this, right? So that's if we were looking at comparing these two quantities of height versus volume, that's what the bottle would be. Something like that, where it's constant rate of change, but then suddenly you've got a higher constant rate of change because you've got bigger changes. They're still staying equal to each other. That's straight, you guys. That's straight. Okay, and then the changes are, the height is increasing, but the changes in height are decreasing. So that's non-constant rate of change, and we get the curve bends down like this. Okay, so we'll have just a regular assignment over break. And then, what?
So we'll do Tuesday during break or Tuesday?
No, it'll be due Tuesday when we get back.